Let's go live. All right. Good afternoon and welcome to MAE 113, Calculus for the Liberal Arts. My name is Richard Kaur and this is Lecture 18. And in today's lecture, we're going to cover section 3.3 in the textbook. So, and just got to make sure that the audio is okay. So again, thumbs up if you can hear me, and also, excellent, good. All right. So, what for those that kind of want the executive summary, basically, what today's lecture is that the sign, which means that it's either plus or negative, of the second derivative this indicates that it's, what the shape indicates which way the graph of the function is bending. So if you know that, basically that's what we're covering, and you can passively listen to this. Or if you don't know what I'm talking about, let's look at two things. Let's look, for instance, at this. So let's look at here. And again, if there's questions, make sure you put them in the chat. Hopefully someone notices it. There is about a 30-second delay. So again, just to remind you that if I don't see it immediately, somebody else might see it in the chat and they might go, yes, we've covered this before. No, we haven't covered this before. Or that's a very good question. Or did I just drop another negative sign? These are all very important things, especially in math. Okay, so I'm going to draw two. I drew two axes, and what I'm going to have is they're both going to be increasing functions. And remember, increasing means that the values are going up as the y values are increasing as the x values are increasing. So that's an increasing graph. And I will pick something over here. I will have points A and B. Excellent. So I said I was going to make this an increasing graph. So I can have something like this. Didn't mean to stutter. So I can have that kind of a graph. That's increasing, right? Or I could have something like this. Now, why do we care about what the graph looks like? Again, it depends on the context of the problem. For instance, if you're running a company, again, I keep thinking that we're all economics or we're business admin here. So we're running a company. This is the kind of growth that we want. We want it to keep growing bigger, faster. So it's increasing. This would say, yes, our company is increasing, but we're going to hit an asymptote, or we're going to hit a ceiling, or basically we're slowing down, and we could be approaching where we could have it switching from increasing to decreasing, right? The rate at which the function is increasing or decreasing. Yes. Yeah, that's what we're going to be looking at. So it's the rate at which the function is increasing. So again, these are both increasing functions. This is an increasing function. What does that mean? That means that the derivative is positive. But we need something else to be able to distinguish it between these two, right? This is, if this was a company, again, like here's an example. In a company, you know, this is good. You know, there's still more growth to be had. It's still growing. It's increasing. And there's growth. It's, you know, this was a company. Yeah, sure, it's increasing, but it's slowing down. You know, this could be a product. It could be like the minivan, right? Everyone, basically, we get to market saturation. It starts to slow down. Everyone's got one. Now we need to come up with something different. What else could we be? You know, this is an example. How about COVID? You know, if the number of cases are increasing, yeah, okay, we expect people to keep getting infected. But, you know, is it doing this kind of increase? Like, is it keep growing? Or is it somehow, you know, is it bending, you know, kind of reaching kind of an asymptote? Again, we want to know. And so this is about the increasing. And as Maple has already alluded to it, we are starting to look at the second derivative of that. So when we start to look at the tangents here, you know, we have a tangent here, and we have a tangent here, and we have a tangent here. We're looking at these, and the rate at which these are, you know, getting bigger, so the rate of these tangents is actually positive. And if we look over on this side here, I draw little tangents here just to give you an idea. These are the slopes. We're looking just at the slopes. You can see that the slopes are decreasing. So the rate at which these are, the rate of the slopes are decreasing. So we can start to look at, you know, kind of these, the rate of increase. This is positive. And here, these are the rates of increase. That is, it's negative. It's a negative. It's decreasing. Okay. So we have two terms for this. When it's increasing and it's going up like this, this is what we call, I'll write it here, concave up. And this one is called concave down. So that is why we get the word convexity. Now in this one, so what we see here is that all of the graph, you know, this function here that I've driven in black, it lies above the tangents in the interval. And same thing for this one. All of the graph lies below the tangents in the interval. Okay, so what else are we going to look at? And I'm going to tell you that when we look at this, we're looking at when it's concave up, if this is the function, and I'm going to call it, this is, call this y of f of x, then, so I've written it up here, it's concave up when the derivative, the second derivative, of course, is positive. And when I look over here, so I have y equals f of x. Now we're looking at the second derivative. This is where it's concave down. And that is negative. Okay, so I've kind of done just a little bit of, sketching, but let's use some real functions to kind of illustrate this. And by real, I mean just, functions that we kind of recognize. So let me start off with this one. So we'll start off with the parabola. Here's a sketch. And I'm drawing it on the interval from 0 to 1. Or from 0 to infinity, I guess, because I got arrows on it. So we already know that it's increasing on that interval from 0 to infinity. And of course, we can check that out by doing the derivative of that. So using our first derivative, taking the derivative of x squared, that's just 2x. And that's positive on that interval. So whatever, I'm putting a positive value in here. A positive value times 2, it's still going to be positive. That's always going to be greater than 0. So that's why it's increasing. And then we'll say that we'll look at the second derivative. So d squared y by dx squared. And this is nice because the derivative of 2x then is just 2. And that is always positive because 2 is always greater than 0 on that interval from 0 to infinity. And since that is positive, y equals x squared is concave up on that interval from 0 to infinity. Maybe, okay, I'll keep that there. Let's have to make sure that let's draw another one. Okay, so we can have a function that is got to be increasing, and it has to be, we kind of wanted the concave down, so I'll draw this. And that function is y equals square root of x. Now it's also increasing on 0 to infinity. And if we also checked if it's increasing, let's do, we have square root of x. We're just going to rewrite this as x to the 1/2. And then if I take the derivative of that, it becomes 1/2 x. The 1/2 drops down by 1, so I get minus 1/2. So I'm left with 2 square root of x. Now again, if I put in any number from 0 to infinity, this is still going to be positive. This has got to be, the domain of this has got to be positive. So, and the range of this is positive. I have 1 over 2 times a positive number, so that again, that's just going to be greater than 0 on 0 to infinity. So what we've shown there is, yes, it is increasing on that interval. But what about the concavity? So we're going to take the derivative of this. I have my half out in front. The negative 1/2 comes down in front. And then I have x to the minus 1/2, and I got to subtract 1. So it's minus 1/2 minus 1 gives me minus 3/2. So that's equal to minus 1 over, I have 4 to the square root of x cubed. Again, this, we're looking at the interval for x from 0 to infinity. So again, this is going to be positive, this is positive, this is still positive, and then we have that negative. That negative will make the whole thing negative, so it's less than 0 on 0 to infinity. So that means y equals the square root of x is concave down on the interval 0 to infinity. And again, it just depends on what the application is. Like this would be good for COVID. Like we see that it's increasing, but it's slowing down. But or this is good for business. We see it's increasing and it's getting bigger. So the concavity helps to distinguish kind of that bend in the graph. So here's the test for concavity. So everyone's okay with what I've done on the paper so far? What's I don't see any questions. That's either good or bad. I'm not sure. I'll have to flip a coin. Okay. No coins are available, so I'm just going to summarize this. That if the second derivative is greater than 0 for all x on an interval, then the graph of f is concave up. And again, if it's negative for all x, then the graph of f is concave down, concave down. Now, again, this implies that concavity can switch. Doesn't have to, but it could. And where the concavity switches, so where it switches, those are points of inflection. So those are points of inflection. So there's a term, I'll just kind of put it in a box. And possible candidates of points of inflection is where the derivative, the second derivative, is equal to 0. Now again, it has to be, for a point of inflection, it has to switch. So it has to go from either concave up to concave down or vice versa. But you could, for instance, have the derivative equals 0 and then it actually stays the same. So it could be concave down and then still concave down. So let me just, before we get into the really interesting examples, I'll use kind of more of an illustrative one. So let's go with 3. So again, the concavity is kind of trying to describe the bend of the graph. Okay. So I have this, points of inflection. So let's go with, here's an example. So show that y equals x cubed has an inflection point at x equals 0. So again, I'll just use my f notation here, my functional notation, and just use x cubed. If I take the first derivative, that's 3x squared, and taking the second derivative, that's 6x. Now we want to see if it has a inflection point. So the inflection point is where it could be at x equals 0. So I have, so that's the inflection point. So I'll put in 6x equals 0, x equals 0. So yes, it is possible that we have an inflection point there, but I need to check at 0 what it's like around it. So I need to check the concavity around it. So to do that, I'm going to do a test point here. So I'm going to pick f prime and something in that interval. I'm going to pick -1. So I got 6 times -1 gives me -6. So that is less than 0. So again, this is concave down. And for this one, I have 6 times 1. So that's equal to 6, which is positive, which means that this is concave up. So yes. So since it switches from concave down to concave up, x equals 0 is an inflection point. I almost wrote inflection point. So we've done that one. So let me see if, here's an example where the second derivative is 0, but it's not an inflection point. So here's an example. So show that y equals x to the 4th does not have an inflection point. At x equals 0. So again, I'll just kind of write out a couple of times. I have my functional notation at, x to the fourth, and then I'll take the first derivative. So that's 4x to the 3, and taking the second derivative, I get 12x squared. So setting that second derivative equal to 0, what I have is 12x squared equals 0. Dividing 12 on both sides, I get x squared equals 0, or x equals 0. So this is my candidate. But if I pick my value here, I have f double prime at, let's pick -1. Then I get 12 times -1 squared. It's that squared that's going to make it positive, so I get 12 times 1, which is 12, which is greater than 0. So again, this is concave up. And then over on this side, I have this equal, this is at 1, let's pick that, something easy. And again, 1 squared, that's still 1, 12, and that's still greater than 0. So again, this is concave up. So then kind of my conclusion is, since it does not switch concavity around x equals 0, x equals 0 is not an inflection point. Okay, so again, here's 2 examples. Oh yeah, maybe if you're visual learners, let me just kind of give you a quick sketch. We kind of know what a cubic function should look like. So here's a cubic function, and it'll kind of go up like that. Here it goes down. Here's x, and here's y. And again, we can look at this. We can see that this function is increasing over the entire domain. And we can see that this is concave down, and then it switches concavity, and it goes concave up. Over on this side, this is x to the 4th. So drawing a quick sketch of that. It's always going to be positive, so I'm not going to draw some negative values for that y. But it kind of looks like this, and then kind of goes up like that. Oh, and I should label. So here's that point. Here's that point of inflection. And that is not a point of inflection. Okay. Is there any questions about that so far before we pick maybe a little bit of a different function? Okay, maybe we'll take it a little bit slower. Let's do number 4. So we have an example, and let's use f of x is equal to x cubed minus 3x squared plus 4x minus 5. And so we have to, questions would be like, where is it? Concave up or concave down? On what intervals? And then, B would be like find inflection points. And really, if we do our work, we kind of get B for free because we'll see we have to find where it's concave up and concave down, and where it does switch, then we'll be able to say explicitly that those are points of inflection. So if we start with A, I'm just going to rewrite that out again. So we need the second derivative to find the concavity. So again, should be doing this along with me, just as a refresher. Being able to differentiate a polynomial is one of the basic goals of this course. We have 3x squared, so then I have 6x plus 4. And I'm going to differentiate this again. So I have 3 times 2 is 6, x minus 6. Now again, this is where Maria would be asking me, like, do we need to simplify? At this point, yes, let's do that. Let's simplify this a little bit, because what we end up having to do is we need to solve for the inflection points too, or where they're interesting. So 6. I know I keep saying Maria, because again, it's a good question. Like, do I need to do more work than I have to? And again, like when I said to her, I said, it depends. This is the point where we do have to simplify, because we need to manipulate it a little bit more. We need to solve where it equals 0, etc., etc., etc. So for this one, it's concave up when it's greater than 0, the second derivative. And for that, I get 6 times x minus 1 is greater than 0. The 6 goes away, so I'm left with x minus 1 is greater than 0, or x is greater than 1. And for it concave down, that's when it's less than 0. So again, very similar argument on the left-hand side. And so I have this. So what you actually get then is that at 1, when we're looking at these intervals, this is concave down, and this is concave up. And so because it switches, x equals 1 is an inflection point. So for that, I've answered A, and I get B for free. Okay. It's always funny because I get to see some of the memes online. And so part of the memes I saw was like, on the exam in the lectures the examples are really easy, and then like the assignments are a little harder, and then like the exam is like a lost treasure map. So let's do something that's a little bit at kind of the exam level, And let's say that I have a function like this, or I give you a function like that. And it usually goes, you know, find the concavity, and find the inflection points. So you see find the concavity, which basically means we're going to have to start doing this. Well, we have to get the first derivative and then the second derivative. So here's the first derivative. And again, we have to then remember our quotient rule. And our quotient rule was, so I have f and g. So these are my f. Here's my f. And here's my g. So it's the derivative of the top times the bottom function minus the top function times the derivative of the bottom all over the bottom function squared. So doing this, I have x. So the derivative of x is just 1 times the bottom function minus, because again it's the minus there, the top function x times the derivative of the bottom function. So I get 2x, and that's it, all over x squared plus 1 all squared. So yes, at this point we do have to simplify just a touch. So I get x squared plus 1 minus 2x squared all over x squared plus 1. So you can also see that I get 1 minus, so I have a 1x squared minus 2x squared, so that's just x squared all over x squared plus 1 squared. Okay, so that wasn't too bad. But yeah, we're going to have to do this again. And again, meticulous attention to detail is important to this. Not only will we have to apply, we have the quotient rule, but we also have this one down here where we'll have to apply the chain rule. So again, taking the chain rule of this, x squared plus 1, like that, the 2 comes down in front, I leave the inside alone, and then I take the derivative of the inside, so I'm left with 2x, and that's it. The inside function is left alone like that. So again, I'll have to remember to use chain rule when I'm taking that derivative of the bottom function. So the derivative of this top function is, well, the 1 is a constant, so that's 0. And then I have a minus, the 2 comes down in front, x, that's it, times x squared plus 1. So just that bottom function, minus 1 minus x squared, times, again, now this is where I have this derivative up front here. So I have a I'll write it like this. 2 times x squared plus 1 times 2x. And then I have this bottom function here. I also like to point out here, this is a very common mistake. Even I have done it when I was doing lectures. that we're going to square this. And so it's not 2, but it's going to be 2 times 2, which is 4. And yes, we still have to simplify this because we have to we have to solve this for 0. So to do that, again, we hope that we can do some factoring or some simplification. And so I will switch to this orange pen here. I see that I have a 2x here, and I also have a 2x here. So that's what I'm going to do. I'm going to pull that out. So I have 2x. And the other one I see is I have this. This is a repetition in here. I only have one of them, so I'm going to factor that one out as well. So just one of those. And then what I'm left with, since I have that 2x in front, I'm just left with that minus. And I still have an x squared plus 1 because that's a squared, so I've taken one of those out. I'm just left with x squared plus 1. Then I'm left with a minus 1 minus x squared because I didn't touch that. And I still have a 2 there as well. And I think that's it. So I'll close off that bracket. We'll write, can't forget about the denominator. And again, we can do a little bit more simplification. So I get a minus x squared minus 1. And then I have minus 2 times, so minus 2 times minus gives me a positive 2 x squared. Everyone's watching, right? Make sure that I'm not messing up any negative signs. Okay, so I have a 2x squared minus x squared, so I'm left with x squared. And then I have a minus 1 and a minus 2 gives me minus 3. Everything's okay? Are we done yet? Well, okay. So there's also one more thing that I can do. I can cancel this one out, and this goes down to a 3. So I'm left with 2x times x squared minus 3 all over x squared plus 1 to the 3. Is that all good? No, yes, yep, okay, good. Sorry, I was having a tea. And what are we going to do now? Oh yes, we're going to solve this for 0. Now, the nice thing about this one is that x squared plus 3, that's always positive for all x in the reals, so that's good. because we have the x squared, and because when I have a negative number in there, the squared makes it positive. I add 1, cube it, it's definitely going to be greater than 0. So that's fine. So I don't have to really worry about that, which means then I just need to know where 2x x squared minus 3 is equal to 0. And that means, because again, I'm looking for candidates for where it's points of inflection. So yeah, I'm looking for candidates, not political candidates. These are different. It's where they're equal to 0. And so again, like I said, this is always going to be positive, and so the only way that I can make that derivative equal to 0 is that if this numerator goes to 0. So I have 2x is equal to 0, which means that x equals 0. So that's one potential candidate. And another one over here, I have x squared minus 3 equals 0, which means that x squared equals 3, or x equals plus or minus the square root of 3. So that's, I have 3 candidates now. The plus or minus square root of 3, and the x equals 0. So at this point we're like, oh, we'll draw our line and we'll kind of split up. I have 0, and then I have negative square root of 3. And over on the right hand side I'll have a positive square root of 3. And square root of 3 is approximately 1.7321. I hope so. What's the last? Let me see. 332. There we go. So here's my calculator, and 3 and the square root. So 7321. Oh, good. Yep, it matches. Excellent. So yes, then we're breaking that up. We have minus. So I'm going from minus infinity to negative square root of 3. I have from minus root 3 to 0. I have 0 to root 3, and then I have root 3 to infinity. Okay. So we are running, I have like a minute and a half. So I'm going to do this really quickly. I'm going to substitute in my values of minus 2. And so what I get from that is 4 1/25. I can substitute in this value in here, which is minus 1, and I get a half. I can substitute in my value here at 1, and I get minus a half. And then lastly, I get here, I'll pick a value of 2, and that's 4/25. So again, this is negative, so that means that it's concave down. This is positive, this is concave up. This is concave down. This is concave up. So again, finding the concavity, it's concave down on minus infinity to square root of 3, or it's also concave down on 0 to square root of 3, and it's concave up on minus root 3 of 0, union square root of 3 to infinity. Would you simply input? Yes. I would personally, that's what I would do, because you know that it's going to be always positive. Yep. So you could just look at the sign of this. So for instance here, I have minus 2. So if I just looked at 2x times x squared minus 3, and this is for at x equals, we'll pick minus 2, I get 2 times 2, so that's minus 4, and then I have the minus 2, which gives me 4 minus 3, and I got 1, which gives me minus 4, so again, that's negative, so again, that's concave down. And since these are switching, x equals minus 3, 0, and root 3 are inflection points. Okay, that's all the time we have today. Thank you for tuning in for this lecture, lecture 18, second derivative and concavity. Remember that tomorrow we have a quiz. There is an assignment that's posted. Please check that out. If there's any questions, feel free to send me an email. You know my email address through the RMC server. And I hope you have a great night. Thank you everyone for tuning in, and I will see you tomorrow. Take care. Any idea when we will receive our test marks? As soon as I'm done marking them. I will, and it's a little slower because I have to, I'm old school. I'll still probably mark everything on paper and then rescan everything back in. So it takes a little bit of time. I hope to have it back by Thursday. Okay, I'll see everyone tomorrow. Take care. Yes, I already got that email. And if somebody misses a quiz or a test, yeah, I'll send you a reply about that. Okay, have a good night, everyone.